Hey everybody, Mr. Field back again with another video. Today we're going to be talking about classifying triangles on the coordinate plane. So that being said, we got some big picture stuff in this unit. It's important to know that once we're on the coordinate plane, we can actually use some old information like the distance formula, midpoint formulas, also the slope formula in order to determine what type of shape and what type of specifically triangles that we have going on here. Do we have right triangles? Are they scalene, acute, obtuse? Um, are they equilateral? We can use information from Algebra 1 and our new skills of distance and midpoint formula in order to actually do this. So right off the bat, right, hopefully you can complete this warm up. We're going to skip past this because I don't want the video to go too long. I'm just essentially hoping that you can use the distance formula in order to solve for the length. However, I do want to talk briefly about slope. So finding the slope between 2 points, very briefly. We have two coordinates, so that's why we organize it as x1, y1 in order to essentially say first x I see, first y I see, and then x2, y2. Using the slope formula, we can realize, well, I'm going to do y2 minus y1, so I'm thinking that should be negative 5 minus 7 in this case, over x2 minus x1, so I'm thinking it should be 2 minus negative 8. You got to be careful with those double negatives. So negative 5 minus 7 should be getting more negative, so I'm thinking we're going to get negative 12. And then 2 minus double negative becomes positive in this case. 2 plus 8, 10. So if we simplify this, we shouldn't be able to divide by 2 since they're both even numbers. We get negative 6 this. Or in terms of rise over run, you could say, hey, well, we're going down 6, right 5. So this would be a negative decreasing slope. So you hopefully should be able to imagine what this would look like, this line specifically, if you were to graph it. Now, why do we care, right? Why do we care about slope? How does that relate to distance and midpoint formulas? Well, in the coordinate plane. Well, the most important things to remember is there's a difference between parallel and perpendicular. So for instance, if I had a line, just change my color here. For instance, y equals negative 6 fifths x minus 2. I know just by looking at the slope here, by comparing them, I know for sure that this line, y equals negative 6 fifths x minus 2, would be parallel to this given slope. So long story short, they have the same slope, they're going to end up being parallel, unless you have a special case where they're actually the same line graphed on top of each other. But in this section, typically they won't be. However, they could also be perpendicular, which means not only do they cross at a right angle. Now, an example of that would be if they have the opposite reciprocal slope. Opposite meaning, we'll notice our original slope is negative, so our answer will have to be positive. Reciprocal meaning the flip, so we would have something like y equals 5 6x plus 4. I would know if I compared these lines, right, that they're definitely going to intersect, and they're definitely going to intersect and form a right angle. Now, what is that, or why does that help us? What implications does it have for us? Well, typically, if you have perpendicular slopes, you're going to end up with a right triangle. Otherwise, it could be acute or obtuse. So knowing how to find slope, knowing how to use the distance formula, really important in this section. So let's just slide down with some brief overviews. So you might even want to pause the video and try this yourself before you just jump right in. The most important part here is the description. So before you even try these problems, there's a couple strategies we can use in order to solve them. So for instance, we know the definition of an equilateral triangle is a triangle that has all three sides that are congruent. So how would you actually use the distance formula or midpoint formula or the slope formula in order to confirm for sure that an equilateral triangle is in fact equilateral, that all sides are the same? Well, unfortunately, you'd have to just use the distance formula 3 different times. And if all the answers are the same distance, right? So if I call this like A, B, and C, so the distance from A to B is the same as C to B is the same as A to C, then you can say, yep, it's got to be equilateral. Now, if we think back to isosceles, we could do that as well. Isosceles means two things, two sides and two angles are equal. Now, considering we don't have a tool to measure angles on our computer, we can't check the angles to confirm that they are in fact equal. If it's just 2 of the angles are equal and the last third one, the vertex angle up here, wasn't, we could say it's isosceles. However, using the tools that we have, we're going to have to use the distance formula times 2. essentially confirming, hey, again, if I call it ABC, the AB and BC are equal, and that AC is different, right? So, I mean, at least times 2. If you actually graph it on the coordinate plane, that actually helps too. You can maybe, for instance, count these, but I guess technically, maybe I'm fibbing. Maybe you actually have to confirm and do times 3. So, because again, you can confirm that these two are the same, but if you don't check the third side to confirm that it's different, so yeah, I guess actually we got to use distance formula 3 times again. So feel free to break out that handy dandy calculator. And it's no different for scalene. We're going to have to do distance times 3, baby. Because we have to confirm that all 3 sides are totally different numbers. All right. Again, a lot of this section is actually confirming. I know you can graph or plot these points, connect the dots with lines, and look at it and say, oh, duh, clearly they're not the same length. But part of geometry is being able to justify how you know. And to fully justify it, you have to check the distance formula 3 separate times. Now, in terms of a right triangle, we kind of just talked about it. In order to prove that this is the right triangle, you need to prove that, for instance, this side, which maybe we'll change it up, DE, has to be perpendicular to, let's call it EF. If you can confirm that by comparing the slopes of DE and EF, if they happen to be opposite reciprocals of each other, then we're in business. We know for sure it is a right triangle. In fact, if you really even wanted to get advanced, even more advanced, you could actually confirm whether it's acute or obtuse. Obviously, again, we know you can look at it on a graph and say, oh, duh, obviously it's an obtuse or an acute angle. It's pretty obvious. But if you really wanted to check, here's something we're going to talk about later. It's all about c squared, which is the most important. Remember, Pythagorean theorem is a squared plus b squared equals c squared. But since we're going to prioritize c, which is always the longest side in a right triangle, so looking at this example, this would be the C value, and then we could call DE or EF the A or B. They're called the legs of a right triangle, so A or B, and then C is always the hypotenuse, so get hype, that's the abbreviation for hypotenuse. It's always the longest side. Why? Because we know that the largest side is what's across from the largest angle, and in a triangle, well, you can only have one right angle, because if you have more than one, 90 plus 90, for instance, well, that's already 180 degrees, and that means the last angle would only be 0 degrees, which is impossible. So remember, because of the triangle sum theorem, C would have to be the largest side in this right triangle. So if C squared ends up being greater than A squared plus B squared, a little preview for later, then you can say for sure this is an obtuse triangle. If C squared is smaller than A squared plus B squared, we call it acute. And of course, if C squared is equal to A squared plus B squared, well, then it's the right triangle because it's following the original Pythagorean theorem. So anyway, that's another way. If you really wanted to go deeper, you could confirm that it's acute or obtuse by looking at these. However, for now, we're really just concerned with, is it a right triangle or not? And then, of course, right isosceles, a little bit of work here, right? We not only would have to compare the slopes, so we're doing the same thing, that are their opposite reciprocals, but we would also, I'm just going to use the same picture if that's cool, have to check to see if two of the sides end up being congruent and being the same length. So you have to use the distance formula and compare the slopes to determine whether it's a right isosceles triangle or not. So it's kind of just an overview of what might happen. So let's jump into a couple examples to show you what's going on. All right, so step 1, let's read the directions. We should always do that. It says classify triangle ABC by its sides. So I'm thinking we got scalene as an option, meaning no sides are the same. We got isos. Hopefully you're cool with me, isosceles, reading that. And of course we have equilateral. So those are our 3 options based on these 3 vertices, these 3 vertexes for ABC. So step 1, I'm just going to plot the points. Looks like point A is right smack dab at the origin, 0, 0. Looks like point B, 1, 2, 3, 1, 2, 3. So here's A, here's B, and finally C looks like it is negative 1, 2, 3, up 1, 2, 3. So by connecting the dots here, we clearly have a triangle. Well, that was strange. One sec, folks. See if I can bring back that point. We definitely have a triangle. But just by looking at it, so this is C. Depends on what you want to check first. It actually might be a right triangle. This angle right here, I'm gonna put a question mark with, angle A, looks like it's possible that it might actually be a right triangle. So I know it's like, we're kind of skipping to the next step, but I actually kind of want to do that first because if it's a right triangle, that creates a little bit less work for me in terms of checking all the sides, because we know if it is indeed a right triangle, we know in this case the side across from it, CB, would have to be the largest side. So that already eliminates the option that would be an equilateral, because you can't have an equilateral right triangle. So in fact, I'm actually going to skip to step 3 if that's cool with you, and then we'll slide back. So let's check for right angles by checking the slopes. So the slope of AB, all right? This section's pretty straightforward, I think, folks, but the most important thing is to stay organized. So we're checking between points A and B. So I'm going to go and actually write points A and B. We know it's 0, 0, and we know B is at 3, 3. It can't hurt to write it out. And then if you really need to, we know we can say, hey, x1, y1, first x I see, first y I see, x2, y2. It's important to stay organized. And then the actual slope formula is slope n is y2 minus y1 over x2 minus x1. So let's plug in what we know. We're going to do y2 minus y1, which is 3 minus 0, over x2 minus x1, which is, again, 3 minus 0. So it looks like between A and B, the slope would be 3 over 3, which is 1, a slope of 1. Now, we can confirm that graphically, by the way, too. If we're going from A to B, it looks like a up 1, right 1, ding, 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 up 1, right 1, ding, 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 up 1, right 1, ding, ding, ding. However, I always ask my students, should we trust the graph or should we trust the math? You should always trust the math, especially because human error. What if you graphed it wrong? Of course, you could visually check to make sure it makes sense, but we should always trust the math over the graph just to confirm. All right, so that being said, let's find the slope of, for instance, CA. Let's go straight to CA. I know it's the last one, but if we can confirm, notice this is a slope of 1, so, or really 1 over 1. If we can get a slope of negative 1 over 1, which is the flip, right? Flip the ones, and then one's positive, one's negative, opposite reciprocal, then we know that they are perpendicular, which means this is a right triangle. So I'm actually going to skip to the slope of CA. So let's check that out. So from going from C to A, step 1, let's stay organized. Let's write the coordinates. So from C to A, we'll do it in that order. We have negative 3, 3, and 0, 0. Following the same formula above, we can say, well, we can do y2 minus y1. And again, I'm going to organize x1, y1, x2, y2, just so I don't make a mistake. It's actually easy to do if you rush. So I'm going to say y2 minus y1, which would be 0 minus 3, over x2 minus x1, which would be 0 minus, I'm going to put a parentheses here, negative 3. I like to do that little parentheses just to remind myself it's double negative. So up top, 0 minus 3 is negative 3, and double negative should become plus positive, and we end up with negative 3 over 3, which gets us negative 1 over 1. So we have just confirmed, yes, sir, these are perpendicular. So I know for sure that this is at minimum, a right triangle before even moving forward. It's got to be a right triangle. In fact, I don't even really have to check the slope of B to C because I've already confirmed that's a right triangle. So it's saving me some time by checking that first. And also, if you notice, from C to B, just looking at it visually, this is a flat slope. We should end up with a slope of 0 if you were to check that, because this is a flat line. There is no increase, there is no decrease from C to B. It's not going up, not going down. So it would kind of be a waste of time to do that. A lot of this course is trying to work smarter, not harder. So again, I checked the two slopes that were reasonable by looking at the picture after graphing it, and it's clear that these are perpendicular. So I know it's a right triangle. However, I'm not done. We have to confirm, right? We have to confirm whether or not AB is equal to AC. If they are equal, then we can say this is an isosceles right triangle, also known as a 45-45, 90. Obviously, just by looking at the picture from C to B is just a smidge longer than the other lines, because we can literally count 1, 2, 3, 4, 5, 6. So I'm thinking the other two sides, they might be the same. They might be 1, 2, 3-ish, 1, 2, 3-ish, but let's actually confirm, because again, we should always trust the math, not the graph. All right? So let's check AB and AC. We're not even going to really confirm BC because we kind of already know the distance because it's literally straight across the grid. So let's try A to B. Again, I'm going to write the points down so I don't make a mistake. Looks like 0, 0, and we have 3, 3. I'm going to organize myself, x1, y1, x2, y2, just so I don't make a mistake. And in this case, I'm going to write the formula down, which we know the distance is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. And we're going to plug in what we know here. So I'm thinking, well, we're going to end up with, and by the way, a lot of this is just calculator work from here, but I really do need to see this first step, what you substituted in. Again, showing your work from there on out is really your decision, but the more work you show, the more points you typically get, especially if you make just a tiny mistake. So anyway, let's plug stuff in. So we're going to do x2 minus x1, which I'm thinking should be 3 minus 0, whole thing squared, plus y2 minus y1, which again would be 3 minus 0, whole thing squared. From here, it's kind of mental math or calculator work, but you should get 3 squared plus 3 squared, which is 9 plus 9, which is the square root of 18, if I didn't make any mistakes. So, again, if you wanted to grab your calculator, we could approximate this. Just to be sure, we could type in second root 18, get approximately 4.24. So keep in mind, when I was just counting, I thought it was actually 3. So when I was counting this, I said, hey, oh, this is a distance of 1, 2, 3. But it actually turns out to be a little bit more. It looks like 4.24. So we got to be careful. It's basically what I'm saying. So it looks like the distance from A to B is 4.24. Let's check out from C to A again and see if they're the same or different. So from C to A, I'm going to rewrite it, right? Negative 3, comma 3, and then we have 0, 0 for A. We got x1, y1, x2, y2. We're going to substitute it into the same distance formula. So I got to see this first step, what you plugged in where. So x2 minus x1 should be 0 minus negative 3 squared. Notice I'm doing that double parentheses here. I'm doing this parentheses to make sure I remember it's double negative. So that's the hardest, or sorry, that's the easiest place to make a silly mistake when you're doing these, is not staying organized and being careful of double negatives. And of course, we're going to do y2 minus y1, which I'm thinking would be 0 minus 3 squared. So that should get us plus positive, right? Which gets us 3 squared again, plus 0 minus 3 gets us negative 3 squared, but it won't matter because the positive 3 squared, when you square something, you always get a positive answer. So we're going to end up with the square root of 18 again. 3 squared is 9, plus negative 3 squared is, well, 9. Double negative becomes positive. So we end up with the square root of 18. Again, we already know, it's 4.24. So not only is this a right triangle, we have just confirmed this is an isosceles right triangle. All right, so what I'd like you to do is scoot on to the next example and give it a try. Plot the points, try and determine what type of triangle is classified as based on its side lengths. Again, we have scalene for that option, which means none of the sides are the same, isosceles, which means 2 of the sides are the same, and of course equilateral. And then finally, try and determine whether or not it's a right triangle. If it is a right triangle, right, you can confirm that by checking the slopes of 2 of the sides. If it's not, you technically could go further and determine whether it's acute or obtuse by using those formulas that I talked about earlier. But I'm not super concerned about that. I really, at the moment, just want to make sure you can plot these points and determine, classify the triangle based on the sides and angles. Thank you for watching.